Hello students, in this chapter we are going to study the mass and energy analysis for the control volumes. So we will be dealing with the steady state, steady flow process and uniform state, uniform flow processes in particular. From the practical experience we come to know that different amount of energy is required to raise the temperature of identical masses of different substances by 1 degree. For example, 4.5 kilojoule of energy is required to raise the temperature of 1 kg of iron from 20 degrees Celsius to 30 degrees Celsius. Whereas 9 times this energy, that is 41.8 to be precise, is required to raise the temperature of 1 kg of liquid water by the same amount. It means basically there is a certain property which enable us to compare the energy storage capabilities of various substances. This property is nothing but specific heat. The specific heat is defined as the energy required to raise the temperature of a unit mass of substance by 1 degree. Now, if we talk about specific heat, there are two types of specific heats particularly: specific heat at constant volume and specific heat at constant pressure. The specific heat at constant volume, CV, it is basically seen as the energy required to raise the temperature of the unit mass of a substance by 1 degree while volume is maintained constant. Now the energy required to do the same while pressure is maintained constant is known as specific heat at constant pressure. Now I would like to tell you that Cp is greater than Cv. We will prove it with the help of mathematical operations in the chapter that while we will be dealing with the property relations and Maxwell relations. But even we can think logically that how Cp is greater than Cv. Mathematical things are different things that we are going to prove at later stage. But logically, why Cp is greater than Cv? Because at constant pressure the system is allowed to expand, and the energy for this expansion must also be supplied to the system. That is why Cp is greater than Cv. Now we want to understand and we want to express the specific heats in terms of other thermodynamic properties. So what we can assume that we take up a fixed mass in a stationary closed system and say it is undergoing a constant volume process. When it is undergoing a constant volume process, it means it is not involving any boundary work, means no expansion, no compression work is involved. So what can you say? That basically whatever energy transaction is taking place with this stationary closed system, means in the form of heat or any other energy, it is basically going to change its internal energy, and this change in internal energy is going to be equal to CVDT. Now applying conservation of energy principle for a fixed mass in a stationary closed system that is undergoing a constant volume process, we can say that the change in energy, which is equal to the change in internal energy, is equal to CVDT. So this gives me the definition of CV, which is nothing but the change in internal energy per change in the temperature when volume is kept constant. Similarly, the specific heat at constant pressure can be obtained by considering a constant pressure expansion or compression process instead of constant volume. And for this we can say that Cp is equal to the change in enthalpy per unit change in the temperature when pressure is kept constant. Now this Cp and Cv, they are expressed in terms of other properties, and it implies that they are themselves property. And like any other property, the specific heats of substance depend on the state, and it has to be fixed by or specified by two independent intensive properties. That is, the energy required to raise the temperature of substance by degree is different at different temperatures and pressures. But this difference is usually not very large. Now, these equations, that is Cv is equal to del U upon del T when V is constant, and Cp is equal to del H upon del T when P is constant. Now, these equations are property relations, and they are independent of the type of processes. They are valid for any substance undergoing any process. The only relevance Cv has to be a constant volume process is that Cv happens to be the energy transferred to a system during a constant volume process per unit mass per unit degree rise in temperature. That is how the value of Cv has been determined. This is also how the name specific heat at constant volume was coined or was originated. Similarly, the energy transfer to a system per unit mass per unit temperature rise during a constant pressure process was known to be Cp, and that is how the value of Cp can be determined, and also explains that how the specific heat at constant pressure term originated. We can also analyze that Cv is related to the change in internal energy and Cp to the changes in enthalpy. It would be more proper to define Cv as the change in internal energy of the substance per unit change in temperature at constant volume. And similarly, Cp is defined as the change in enthalpy of a substance per unit change in temperature at constant pressure. So we can say that Cv is the basically measure of the variation of internal energy of a substance with temperature, and Cp is a measure of the variation of enthalpy of a substance with temperature. Now, an ideal gas is defined as a gas whose temperature, pressure and specific volume are related by this expression, that is PV is equal to RT, where P is the pressure, V is specific volume in meter cube per kg, R is the gas constant, and T is the absolute temperature, that is temperature in Kelvin. Now, Joule demonstrated mathematically and experimentally that for an ideal gas, the internal energy is function of temperature only. Its mathematical part, that is mathematical derivation, we are going to do while we will be doing the chapter of property relation. So it can be said that U is function of temperature only for an ideal gas. Using the definition of enthalpy, that is H is equal to U plus Pv, and the equation of state for an ideal gas, that is equal to Pv is equal to RT, we obtain H is equal to U plus RT. Now R, a gas constant, is a constant, and as we have discussed earlier, the internal energy is function of temperature only. So it will lead to the conclusion that enthalpy of an ideal gas is also a function of temperature only. And in the coming chapter, dealing with the property relations, we will discuss, and we are going to prove it mathematically, that internal energy as well as enthalpy of an ideal gas is function of temperature only. Since U and H depend on the temperature of for an ideal gas, the specific heat Cv and Cp also depend at most on temperature only. Therefore, at a given temperature, U, H, Cv and Cp of an ideal gas have fixed values regardless of the specific volume or pressure. Thus, for ideal gases, the partial derivatives Cv is equal to del U upon del T when V is constant, and Cp is equal to del H upon del T when P is constant. These partial derivatives can be replaced by ordinary derivatives. The differential changes in internal energy and enthalpy of an ideal gas can be expressed by the following relations, that is d is equal to Cv dt and dH is equal to Cp dt. Now the variation or the change in internal energy or enthalpy for an ideal gas that is taking place during a process when the substance is changing its state from 1 to 2, they can be determined by integrating these equations. That is equal to delta is equal to integration of Cv dt and delta H is equal to integration of Cp dt. Now to carry out these integrations, one need to have relation for Cv and Cp as a function of temperature. At low pressure, all real gases approach ideal gas behavior, and therefore their specific heats depend on temperature only. The specific heats of real gases at low pressure are called ideal gas specific heats or zero pressure specific heats, and are often denoted by Cp0 and Cv0. Accurate analytical expressions for ideal gas specific heats based on direct measurements or calculations from statistical behavior of molecules, they are available, and they are given as a third degree polynomial as appended in many of good books. The use of ideal gas specific heat data is limited to low pressure, but these data can also be used at moderately high pressure with reasonable accuracy, as long as the gas is not deviating from ideal gas behavior considerably. These integrations, they are though straightforward, but they take time. These are time consuming, and that is why they sound somewhat impractical. To avoid all these hectic calculations, U and H data for number of gases have been tabulated over small temperature intervals. These tables are obtained by choosing an arbitrary reference point and performing integrations, treating state 1 as the reference state. In many of the ideal gas table that you may find in books, 0 Kelvin is chosen as the reference state, and both enthalpy and internal energy are assigned the 0 values at 0 Kelvin. Please remember one thing, these relations that are given on the slide for delta U and delta H, they are not restricted to any kind of process, they are valid for all processes. Means the presence of constant volume specific heat Cv in the equation does not mean that this equation is valid for a constant volume process only, or the presence of Cp in an equation should not lead one to believe that this equation is valid only for constant pressure process. So we can say that there are basically three methods to determine internal energy and enthalpy change of an ideal gases. If the tabulated U and H data are available, then one can use that, and because that is the easiest and accurate way. Second method could be by using Cp or Cv relations as a function of temperature and performing the integration. Means you can have the polynomial third degree polynomial equations available, and you perform the integrations. This is somewhat inconvenient for end calculation, but if you can suitably program it, then it's quite desirable, and you can have very accurate results by that. Third method could be by using average specific heats. This is very simple and very convenient too when property tables are not available. The results obtained are reasonably accurate if the temperature interval is not very large. So normally, while doing calculations for engineering thermodynamics at the elementary level of BTech program, we definitely go for the third method, that is, we use average specific heats as they are provided in the books, or they are provided in the question paper in the examination. Now the special relationship between Cp and Cv for ideal gas can be obtained by differentiating the relation H is equal to U plus RT. which yields the following result. That is, you replace dH by CpdT and du by CvdT, and dividing the resulting expression by dt, we obtain Cp is equal to Cv plus R. And this is the expression that you must have been using since your class 11th or 12th. Okay, while we will be dealing with the chapter of property relations, we are going to prove it again by mathematical operations. On the molar basis, it can also be denoted by Cp is equal to Cv plus Ru, where Cp and Cv here in this equation, they are the specific heats on molar basis, and Ru is nothing but universal gas constant, whereas in the upper equation where it is written Cp is equal to Cv plus R, that is gas constant. Now the ratio of specific heats, that is having the value of somewhat 1.667 for monoatomic gases, and for the diatomic gases, most of them, they bear the value of gamma equals to 1.4 at room temperature, for example air. Many of the substances that are used in engineering thermodynamics or thermal engineering, they are available in different phases like solid, liquid, vapor or gas. Now you know that if a substance whose specific volume or density is constant, you call them incompressible substances. The specific volume of solids and liquids, they remain constant during a process. Therefore, they are considered to be incompressible substances. So therefore, liquids and solids, they are approximated as incompressible substances without sacrificing much in accuracy. The constant volume assumption should be taken to imply that energy associated with constant with the volume change is negligible compared with other forms of energy. And moreover, while dealing with the chapter of property relations, we will be proving that the constant volume and constant pressure specific heats, they are identical for compressible substances. We are going to prove it mathematically. So basically for solids and liquids, the subscripts like Cp and Cv, they are not used. Instead, we use C as specific heat, means it is not bearing any subscript. The specific heat for solids and liquids, it is written as merely C. It is not bearing any subscript like it is having in the case of gases like Cp or Cv. Similarly, as in the case of ideal gases, the specific heats of incompressible substances, that is solids and liquids, they also depend on temperature only. So the partial differential in the defining equation of Cv can be replaced by ordinary differential, and thus we can write du is equal to C dt, where C is the function of temperature. Now the variation of specific heat C with the temperature should be known to us before we carry out this integration. Now for small temperature intervals, C value at average temperatures can be used and treated as a constant, and therefore we can write this as delta U is equal to Cv average into temperature difference, as we have written on the slide. Now using the definition of enthalpy, H is equal to U plus PV, and remembering this thing that specific volume is constant for incompressible substances, the differential form of enthalpy change for incompressible substance can be determined in this way. So you can say dH is equal to du plus vdp plus pdv. Now this is going to be du plus vdp. Why? Because The third term PdV has vanished as V was assumed to be constant for incompressible substances. Therefore, delta H is equal to delta U plus V delta P. So this can be written as C average into delta T plus V delta P. Now for solids, the term V delta P is insignificant, and therefore you can write delta H, which is also equal to delta U, that is equal to CV average into delta T. Now for liquids, normally we encounter two special cases: the constant pressure process, as we see in the case of heaters, where delta P is 0, means there is no pressure change, or you can say heating takes place at constant pressure. So in these devices, you can say that delta H, which is equal to delta U, is approximately equal to C average into delta T. The other case is related to constant temperature process, as in the case of pumps, where delta T is 0, means processes are taking place isothermally. In those cases, you can say delta H is equal to V dP. Many times one wishes to use the first law in the form of rate equation, which is expressing either the instantaneous or average rate at which energy crosses the control surface as heat and work, and the rate at which energy of the control mass that is varying. Now we consider a time interval t during which delta Q crosses the control surface, means heat transfer is taking place and that is crossing the control surface. Delta W is the work done by the control mass. So this is also like the heat transfer that is crossing the boundary that is separating the system and surroundings. So we can say that is delta W is denoting the work done by the control mass. Delta U is the internal energy change, and delta Ke and delta Pe are denoting the changes in kinetic and potential energy respectively. So you can say the first law can be written as delta Q is equal to du, or you can say delta U plus delta Ke plus delta Pe plus del W. Now we divide all the terms by delta T, and we have the average rate of energy transfer as heat and work, and also increase of the energy of the control mass. Now we take the limit for many of the quantities. As delta T is approaching 0, we have limit for delta Q upon delta T, where limit is delta T is tending to 0, we have Q dot, that is rate of heat transfer. Similarly, for the work we are having this, and we get the power, because the transfer rate of work is said to be power. Similarly, we are having the limiting strategy for internal energy, kinetic energy, and potential energy. So applying all these, we get the first law equation, or the conservation of energy equation, as a form of rate equation as shown on the slide. So delta Q is equal to du plus dt plus d of Ke upon dt plus d of Pe upon dt plus W dot. So all the terms are basically expressed as rate parameters, rate quantities. Now if the change in kinetic energy and potential energy is neglected, then the first law equation can be written in the form as expressed by the last equation. So now we will be discussing conservation of mass and the control volume. Control volume is a volume in which one has interest for a particular study or analysis. The surface of this control volume is known as control surface, and it basically consists of a closed surface. The shape and size of the control volume is arbitrary, and it can be so defined so as to suit the analysis that we are going to do. The surface may be fixed or it may be movable, means it can expand or contract, but the surface has to be defined relative to some coordinate system. Mass as well as energy, whether heat or work, it can cross the control surface, and the mass in the control volume as well as the properties of this mass can change with time. During a time interval del t, the mass del mi enters the control volume and the mass del me leaves the control volume as shown in the figure. So in the figure above you can see that mass del mi is entering the control volume, whereas in the figure shown below you can see that mass del me is leaving the control volume. Now we designate the mass within the control volume at the beginning of the time interval as mt. So mt is basically specifying the mass within the control volume at the beginning of the time interval, whereas mt plus delta t is mass within the control volume at the end of this time interval. So from the law of conservation of mass we can say mt plus del mi. Mt is the mass within the control volume at the starting of time interval, at the beginning of the process, where del mi is the mass that is entering the control volume. So that is equal to mt plus delta t plus del mi, where mt plus delta t is basically mass within the control volume at the end of this time interval, and del mi is the mass that is basically leaving the control volume. So this can also be written as net flow into the control volume during the time delta t, which is equal to increase of mass within the control volume during delta t. So basically what net flow has taken into the control volume during this time interval, that is equal to the mass that has entered minus the mass that has left out. So that is del mi is equal to del me, and that is equal to the change of mass or increase of mass within the control volume, that is mt plus delta t minus mt. Okay, so that can be written as now mt plus delta t minus mt plus del me minus del mi is equal to 0. So the law of conservation of mass can be expressed as rate equation as follows, that is mt plus delta t minus mt upon delta t minus del me upon delta t plus del mi upon del t. Okay, that is equal to 0. That is equal to 0 as shown by the last equation on the slide. Okay, I think that second equation on the slide is clear, because it is somewhat like this. For example, take the example of my class. 25 students were sitting at the beginning of the class. So this 25 is equal to mt. Okay, now 7 more students have come into my class. So that is sort of del mi. 7 more students have entered when my class was going on. Okay. And you can say 2 students have left my class. So that is del mi. That is del mi. So if you want to know that what is the net flow into the control volume, net flow into the my class, then that is del mi minus del mi. That is, there is net change of 5 students because 7 has entered and 2 has left. So the net change into the class is that of 5 students. Okay. And what will be mt plus delta t? That will be basically 30. That will be 30. So if you see the right hand side term, so mt plus delta t, which is equal to 30, and mt, which is 25, so that will also give 5, right? So I think this is clear now. Now mcv is the instantaneous mass inside the control volume. So basically, when you have put limit of delta t tending to 0, then mt plus delta t minus mt upon delta t will become dmcv upon dt, and that is basically the rate of change of mass within the control volume, instantaneous rate of change of mass within the inside the control volume. Okay, now we also put limit for the masses that are entering or leaving the control volume. Okay, so if we divide del me by delta t and put the limit, that will become m dot e. Similarly, if you put limit for del mi and put the limit delta t tending to 0, then that will be m dot I. So basically, m dot E is the instantaneous rate of flow leaving the control volume across the surface area AE. Means some discrete surface area is there, and through that discrete surface area, m dot is the instantaneous rate of flow leaving the control volume. And same is the case for the m dot I. That is also instantaneous rate of flow entering the control volume across the discrete area that is having the surface area of AI. Now, considering the inflow and outflow across various discrete areas at the control surface, the instantaneous rate form becomes del m dmcv upon dt plus integration of all the outflowing mass streams minus the summation of all the inflowing streams, because there may be certain discrete areas through which the substance is entering the control volume. So that is why we have put summation sign. And similar is the case for the outflow streams also. There may be various discrete areas through which the stream may be going out. So that is why we have put summation sign for that. So basically, this equation shown in the last is dealing with the conservation of mass, and that is why it is known as continuity equation. This form is though sufficient, but sometimes it is this continuity equation is written in the terms of local fluid properties, which we will discuss in the subsequent slide. So here we will express the continuity equation in terms of local fluid properties, as it is widely used in study of fluid mechanics and heat transfer. Consider that a fluid is flowing uniformly inside a pipe or a duct. The fluid moves a distance dx during the time interval delta t, and therefore the volume of fluid crossing the surface area A is ADX. Means this is the basically the volume of fluid that has crossed particular control surface, that is A into dx. Now the mass crossing the surface area A is given by ADX, that is volume of the fluid divided by its specific volume. So we have written del m is equal to ADX, which is volume, and that is divided by specific volume. Now we divide both the sides by delta t and take the limit delta t tending to 0, and we get the final expression. That is, on the left hand side we have the mass flow rate, and dx by dt, when delta t tends to 0, it has become velocity. So A into C upon V, which is specific volume. V is specific volume. So this is the final expression for our continuity equation or mass flow rate in terms of local fluid properties. Now we want to develop the expression for the first law of thermodynamics for a controlled volume, and later we will develop it in the rate equation form. Now, for developing the first law in general form as well as in rate equation form for a controlled volume, we will proceed in the same manner as we have done in the case of developing the equation for the law of conservation of mass in general terms as well as in rate equation form. So the control mass and the control volume are shown in the figure, and it is basically representing the mass, that is system, and the control volume at time t, as well as the second figure is representing the system and control volume at time t plus delta t. Now we consider the changes that take place in control mass and control volume during the time interval delta t, during which the process is happening. So during a time interval delta t, the mass del mi is entering the control volume through the discrete area ai, and mass del mi is leaving the control volume through discrete area ae. It is assumed that del mi has uniform properties, and similarly del mi has uniform properties. Now we assume that the total work by the control mass during the process will be equal to the flow work plus the work that is done by the control volume. So flow work is basically the work associated with the mass del mi and del mi crossing the control surface, whereas del wcv will include all the other forms of work that are associated with the rotating shaft and that crosses the control mass boundary. So the first law of thermodynamics for a control mass, that is fixed quantity of mass, can be written in the form 1q2 is equal to E2 minus E1 plus 1w2. As an average rate equation over the time interval, the first law can be written in this form: del q upon del t is equal to E2 minus E1 upon del t plus del w upon del t. Now, as I told you just now, the total work by the control mass during the process will be flow work plus del wcv, and flow work is basically the work associated with the mass del mi and del me crossing the control surface. Now Et is the energy in the control volume at time t, and Et plus delta t is the energy in the control volume at time t plus delta t. E1, which is representing the energy of the control mass at time t, is equal to Et plus Ei del mi, where Ei is basically the specific energy that is associated with the mass del mi that is flowing into the control volume. Now this E is basically the summation of internal energy per unit mass, potential energy of the system per unit mass and the kinetic energy of the system per unit mass. So basically these all three will lead to EI, and this EI when multiplied by del mi, that will make the total energy inflow into the control volume by the virtue of the mass del mi entering into the control volume. Similar is case with the next expression, which is E2. So E2, which is denoting the energy of the control mass at time t plus delta t, that is equal to Et plus delta t plus EE del mi. Now this EE is representing the specific energy of the mass. So this EE when multiplied by del mi will give the total energy associated with the mass. This E is basically the summation of potential energy of the system per unit mass, kinetic energy of the system per unit mass, and the internal energy per unit mass of the mass that is leaving the control volume. So E2 minus E1 will give us Et plus delta t minus Et plus EE del mi minus EI del mi. Now this term EE del mi minus EI del mi, that is representing the net flow of energy that crosses the control surface during delta t as the result of masses del mi and del mi crossing the control surface. So basically EI del mi is representing the energy inflow and EE del mi is representing or denoting the energy outflow. So the net flow of energy across the control surface was EE del mi minus EI del mi. Now, if we talk about the work, then we can say that PE VE del mi is the work done by the control mass as del mi leaves the control volume. So it is, you can say, the work of expulsion, and it is the positive work, means work is done by the system. Now the PE VE is basically the work per unit mass, and when it is multiplied by mass, so that will give me the unit the work in kilojoule. Similarly is PI VI del mi is the work done on the control mass as the mass del mi enters the control volume. And this is nothing but the work of introduction, means it is the work that is associated when mass del mi is introduced into the control volume. Now the total work done by the system during time delta t, del W is equal to del W CV plus PEV del ME minus PIVA del MI. Now the second term PEV del ME minus PIVA del MI is basically the flow work, means the work associated with the masses del MI and del ME that is crossing the control surface. And the first term is basically including all other forms of work that are associated with the rotation of shaft. Now we divide equation 2.61 and 2.62 by del t so as to express them in rate equation form and substitute them in equation number 2.60. Combining and rearranging, we get the expression as shown by equation 2.63. Now we can express this equation 2.63 in the terms of thermodynamic property known as enthalpy. Now we are having EI plus PIVI as well as EE plus PEV in the equation number 2.63. So E plus PV can be written as U plus PV plus C square by 2 plus GZ, because here E, specific energy, will be equal to U plus C square by 2 plus GZ. So that when added with PV, so that will give us the equation number 2.64. So we have substituted the value of U plus PV by H, and we get the, or we rewrite the equation 2.63 so as it becomes the equation number 2.65 in the terms of enthalpy. Now to reduce this expression to a rate equation, what we consider? We consider that each of these terms as del T is made to approach 0. So the heat and work transfer become heat transfer rate and work transfer rate, as we have done in the case of mass conservation equation. Similarly, the two mass quantities become mass flow rates, that is mi dot and me dot, because del mi divided by del T, when del T is approaching 0, it will become mi dot, that is mass inflow rate. Similar will be the case for the me, means del me when divided by del T approaching towards 0, so that will give us me dot. So utilizing the limiting values to express the rate equation, we again include summation sign on the flow terms. Okay, because it's not the single term that we are having for the stream inflow and stream outflow. We can have many streams across the control surface by many discrete areas, and we can have similarly many stream outflows across many discrete areas. So including them, we come for an equation as we are showing on next slide. So we are having these terms in here. All the terms have been represented in the rate equation form, means the heat transfer rate, mass inflow rate, rate of change of energy of the control volume, and mass outflow rate, and the work transfer rate, that is power. So basically this is the general expression for the first law of thermodynamics as rate equation. There are various engineering devices such as turbines, compressor, nozzles, heat exchangers that operate for longer periods of time under the same condition once the transient startup period is completed and steady operation is established, and they are known as steady flow devices. Now the processes involving such devices, they are represented reasonably by the steady flow process, which means a process during which fluid flows through a control volume steadily. See, the meaning of steady means the thing or the parameter that is not changing with respect to time. Like we say steady friend, it means the friend which was our friend earlier and that is continued till today, means that is not changing with respect to time. So steady flow means the fluid properties can change from point to point within the control volume, but at any point they remain constant during the entire process. The basic assumptions are the control volume does not move relative to the coordinate frame. All the velocities measured relative to the coordinate frame are also velocities relative to the control surface, and there is no work associated with the acceleration of the control volume. Actually, what happens? We assume that control volume is having no relative motion with the coordinate frame of reference. It means they both are moving with the same velocity, means we choose coordinate frame of reference such that it is moving with the same velocity as the control volume is, so that there is no relative motion between them, and by this we get rid of calculating the work associated with the acceleration of the control volume. The state of each mass at each point in the control volume does not vary with time. Now the state of mass is not varying, and that is applicable to each mass, each point mass within the control volume, and that is not varying with the time. It means dmCV upon dt will be equal to 0 because state is not changing within the control volume. So this will be 0. Similar will be the case for the energy. That is why we have put dECV upon dt is equal to 0. When a state is not changing within the control volume, henceforth energy will also not change with respect to time. So by this we get that summation of mass inflow is equal to summation of mass outflow, because when there is no change of mass within the control volume with respect to time, so we get the equation 2.67 from the conservation of mass equation that we have done earlier. Okay, and when we substitute these terms here, we get this final term written as last equation on this slide. The third assumption is as that the mass that flows across the control surface, the mass flux and the state of mass at each discrete area of flow on the control surface do not vary with time. The rate at which heat and work cross the control surface remains constant. Means the mass stream that is entering the control surface or leaving the control surface through some discrete areas. So within that stream, every particle is having uniform properties, and that is not varying with time, whether it is mass flux or any other property, whether it is say specific volume or say velocity or enthalpy. So means these properties, whether enthalpy, whether velocity, they will be same for all the particles of the incoming stream or outgoing stream, as the case is. Moreover, the heat transfer rate and the work transfer rate are also constant. That is not changing with the time. Now, for the steady state, steady flow model, we are having one stream that is entering and one stream that is leaving the control volume. So now we don't need the summation sign for the incoming stream and outgoing stream. So we can simply write the continuity equation as mi dot is equal to me dot is equal to m dot. That is mass flow rate of incoming stream is equal to mass flow rate of outgoing stream, and that is equal to a constant mass flow rate, that is m dot. So now the first law for steady state steady flow can be written as shown by the equation number 2.70. Now here, since mi dot is equal to me dot is equal to m dot, and moreover qcv dot can be written as q into m dot, because q is the heat transfer rate in kilojoule per kg and m dot is kg per second, that is mass flow rate. Similarly, small w, which is work transfer in kilojoule per kg. So w dot cv, which is the rate of doing work or the work transfer rate, that can be written as small w into m dot. So it means every term in equation 2.7 is having m dot. So what we do, we divide both sides of the equation 2.70 by m dot and we rearrange the equation and we get the equation number 2.71. So the steady flow energy equation or the steady state steady flow energy equation that is written in equation 2.71, here every term is in kilojoule per kg. Q, the heat transfer, is in kilojoule per kg. HI, the enthalpy, is in kilojoule per kg. C square by 2, that will also have unit of kilojoule per kg. GZ will also have the unit in kilojoule per kg. Same is the case for all the terms on the right hand side of the equation. Every term is in kilojoule per kg. So you should be careful about the units while doing numerical problems, that every term here in the equation 2.71 has to be in kilojoule per kg. Now, many engineering devices operate essentially under the same condition for a long period of time. The components of steam power plant, turbines, compressor, heat exchanger, pumps, they operate non-stop for months before the system is shut down for maintenance. So we can say these devices can be analyzed conveniently as steady flow devices. So basically now we apply the steady flow energy equation as the first law of thermodynamics for these devices, as well as the conservation of mass, that is continuity equation for these devices. So heat exchangers, as the name is indicating, heat exchangers are basically devices where two moving fluid streams exchange heat without mixing. The fluid may be heated or cooled. It may change its phase, that is from liquid to vapor, means it can vaporize, or it may condense, means it can change from vapor to liquid. The examples are the boiler in the steam power plant, that is an example of heat exchanger, because some fuel is burning and giving its heat to the working substance, that is H2O in the boiler, liquid water in the boiler, and that liquid water gets converted into vapor, that becomes steam. So basically boiler is nothing but a heat exchanger. Also the condenser of steam power plant is an example of the heat exchanger, because the steam that is leaving the turbine, its state is either it is superheated vapor or it is very close to saturated vapor. Now it is being condensed with the help of coolant and it gets converted to the saturated liquid state. So that is again basically phase change taking place, and that is taking place inside the condenser. So condenser is again an example of heat exchanger. The evaporator of the refrigeration system. The evaporator coils are nothing but the freezer coils are known as evaporator coils. Now the refrigerant is flowing through these refrigerator coils. This refrigerant is basically exchanging heat with the substance that has to be cooled. Now the refrigerating is absorbing energy from the substance that has to be cooled. So basically evaporator is nothing but a heat exchanger. Similarly, the condenser of the refrigeration system is also a heat exchanger. The refrigerant, which is at high temperature, higher than the surroundings, that is flowing through the condenser tubes and giving out its heat to the surrounding air. So basically condenser here is also an heat exchanger. You can see the diagram on this slide. Basically here cold water is flowing through the pipes. Now this water flowing through the tubes or pipes, that is exchanging heat with the refrigerant vapors. So basically it is an example of heat exchanger. Though the fluid friction is there in all the heat exchanger surfaces, but even then, for this case, for the sake of simplicity, we assume that there is no pressure drop that is taking place when the fluid is flowing through a heat exchanger. So we assume the process of heat transfer to be taking place at constant pressure, means no pressure drop is taking place. Now heat exchanger typically involve no work interaction and there is negligible kinetic energy change. Moreover, there is no significant potential energy change for each fluid stream. The heat transfer rate associated with the heat exchanger depend on how the control volume is selected. So the steady state flow energy equation is getting reduced basically as Q is equal to plus minus He minus Hi, where H is the enthalpy of the stream that is leaving the control volume and Hi is the enthalpy of the substance that is entering the control volume. Now nozzle and diffusers are commonly used in jet engines, rockets, spacecrafts, and sometimes even our garden hoses. Nozzle is basically a device that increases the velocity of fluid at the expense of its pressure, whereas diffuser is a device that increases the pressure of a fluid by slowing it down, means by decreasing its velocity. So nozzle and diffuser are basically performing opposite tasks. The cross-section or area of a nozzle decreases in the flow direction for subsonic flows and increases for supersonic flows, and the reverse is true for the diffusers. Now the rate of heat transfer between the fluid flowing through a nozzle or a diffuser and the surroundings is very small. Means you can say heat transfer is approximately equal to 0, since the fluid has high velocities and there is insufficient time available for the heat transfer. Nozzle and diffuser typically involve no work. Means if you can reduce this system which is involving nozzle to a pulley weight system, weight is not going to rise. So it means it is involving no work. And the change in potential energy is also negligible. Okay. So basically, but nozzles and diffusers, as they are involving high velocities and as the fluid passes through a nozzle or diffuser, there it experiences large changes in its velocity. So the kinetic energy changes must be accounted while we are analyzing the flow through these devices. So these are the diagrams for nozzle and diffuser. In the case of nozzle, the velocity of the outgoing stream is higher than that of incoming stream, and in the case of diffuser, the velocity of outgoing stream is less than that of incoming stream, and the steady flow energy equation reduces to Hi plus Ci square by 2 is equal to He plus C square by 2. Whether it is steam power plant, gas power plant or hydroelectric power plant, do you know what is the device that drives the electric generator? It is nothing but turbine. In the turbine you are having two set of blades, fixed set of blades which is also known as set of nozzles, or the another one is the moving set of blades, or you can say rotating blades. So the fluid passes first through a set of nozzles, or you can say fixed blades, and here basically it expands the fluid to a low pressure and high velocity, means the entire pressure energy is converted into the kinetic energy. So means at the end of fixed blades or set of nozzles, we are having the fluid that is having high kinetic energy. So basically in the second set of blades or in the moving blades, this high velocity fluid stream is directed on a set of moving blades or rotating blades, in which the velocity is reduced before being discharged from the passage. Means what is happening in the moving blades stage? There is change of angular momentum that is taking place because of the change of direction of the fluid, as well as because of the change in magnitude of velocity. And this rate of change of angular momentum is equal to torque. So basically torque is generated and this torque is transferred to the electric generator, which basically causes the relative motion between the conductor and the magnetic field, thus generating current. So this is how the turbine is working and basically producing electricity for us. Now, turbine is a power producing device. It is basically generating power. Now, compressors are the opposite device of the turbine, and not only compressor, pumps and fans, they are also power consuming devices. So basically these are the devices that are used to increase the pressure of fluid. Work is supplied to these devices, means whether it is compressor, pumps or fans, from an external source through a rotating shaft. Therefore compressors involve work inputs. Even though these devices function similarly, but they differ slightly in the task they perform. The fan increases the pressure of gas slightly and is mainly used to mobilize a gas, whereas the compressor is capable of compressing the gas to very high pressures. Pumps, which are also very much like the compressors, they differ with the compressor only in one thing, that is compressor handle gas or vapors, whereas pumps handle liquid. Otherwise function wise they are similar. Pumps and compressors, they basically increases the pressure of the fluid. Now the function, or you can say that working mechanism of the compressor is reverse of that of turbine. In compressor, the working fluid enters the compressor at low pressure, moving into a set of rotating blades from which it exits at high velocity as result of shaft input to the fluid. The fluid then passes through a diffuser section in which it is deaccelerated such that it is resulting in the increase of pressure. The fluid then leaves the compressor at high pressure. Heat transfer from the turbines is usually negligible and they are typically well insulated. Compression process is assumed to be adiabatic in a rotary compressor, whereas in the case of reciprocating type of compressor, the heat transfer from the working fluid is significant and therefore it cannot be neglected while we are doing energy analysis with the first law. Potential energy changes are negligible for all of these devices. Except turbines and fans, the velocities involved in these devices are usually too low to cause any significant change in the kinetic energy. Means you can neglect the change in kinetic energy, except the turbines and fans. So now you can see on the slides, we are having one example of power producing device, that is steam turbine, in which the working substance is steam and we are obtaining the pressure drop. Means you can see that the pressure of the steam that is entering the turbine is 2 megapascal, means you can say 2000 kilopascal, whereas the pressure of the steam that is leaving the turbine is 0.1 megapascal. So pressure drop is taking place and this pressure drop or enthalpy drop is basically getting converted into work or power. The another example is that of air compressor. The working substance is air and air is being compressed, means its pressure is raised. So you can see the inlet pressure is that of 100 kilopascal, whereas the outlet pressure is that of 600 kilopascal. So and to achieve this compression, there is input of work that is involved there, means external work is supplied to the air, means work is being done on the system to achieve this compression. So steady state flow energy equation reduces to W is equal to HI minus HE. Here we have neglected the heat transfer, but if the heat transfer is significant, then you can consider while doing numerical problems. Now this positive sign holds for the turbine, that is power producing devices, whereas the negative sign holds for the air compressors. It is similar sign that we have put in the case of heat exchanger also. In the heat exchangers, we were also having the heat transfer rate is equal to plus minus HE minus HI, and plus was standing for the boiler or evaporator and negative for the condenser. So similarly, I have put also both signs over here, and positive is standing for the steam turbine and negative is standing for the compressor. Throttling valves are basically sort of flow restricting device that causes significant pressure drop in the fluid. Adjustable valves, capillary tubes, porous plugs, they are familiar examples of throttling valve. In the case of turbine, pressure drop is achieved along with the work. Means work is generated because of the drop in pressure. But in the case of throttling valve, only pressure drop is taking place. There is no work generated. Throttling valves are basically small devices, and flow through them that is assumed to be as adiabatic. For heat transfer to take place, two things are required. Either there is sufficient time available for the heat transfer, or there is sufficient heat transfer area available for effective heat transfer. Now, in the case of throttling valve, neither there is sufficient time available as the process is adiabatic, because adiabatic processes are the fast processes. So neither there is sufficient time available for the heat transfer to take place, nor there is sufficient heat transfer area available. So the process is almost adiabatic. Also, there is no work done, as I have mentioned, and the change in potential energy is also small, means there is negligible change in potential energy. Moreover, the exit velocity is sometimes seen as considerably higher than the inlet velocity in many cases. But if you calculate or if you evaluate the change in kinetic energy, that is insignificant as compared to the enthalpy terms. So basically it is neglected. So the conservation of energy equation for the single stream steady flow devices, it basically reduces to Hi is equal to He, means the process is isenthalpic. So we can say the throttling process is an isenthalpic process, means pressure drop is taking place at constant enthalpy. Throttling process also involves change in phase of the fluid sometimes, and the expansion of the fluid in throttling valve, or you can say in capillary tube in the vapor compression refrigeration system, that is one of the common example. So the slide is showing the schematic diagram of a throttling valve. So you can see the restriction in the flow passage, which is basically causing the pressure drop. So PE will be less than PI. Joule-Thomson coefficient. Now, what is Joule-Thomson coefficient? You can see that basically in the case of refrigeration system, pressure drop is accompanied by large drop in temperature, and that is why they are used in refrigeration systems. See, with pressure drop, there are three possibilities for the change in temperature. Means you can achieve increase in temperature for the pressure drop, or you can achieve drop in temperature for the pressure drop, or the temperature may remain constant. So basically what this Joule-Thomson coefficient actually implies, that we will discuss in the chapter dealing with the property relations. There we will see how we are having two regions, that is cooling region and heating region, for the throttling process. But at this juncture of time, you just remember that for the refrigeration system, this device, means throttling valve, should operate in the cooling region, means it should achieve the drop in temperature for the drop in pressure. So the Joule-Thomson coefficient mu j, which is equal to del T upon del P when H is equal to constant. So basically here del T is also drop and del P is also drop, means we are achieving drop in temperature for the drop in pressure. So these terms is going to be positive for the case of refrigeration systems, means for the capillary tube that is working in the refrigeration system, Joule-Thomson coefficient is going to be positive. And as the throttling process is isenthalpic, you can say Hi is approximately equal to He. Now, because H is equal to U plus PV, so you can express this equation in the form Ui plus PIVI is equal to UE plus PEVE. So if the flow energy increases during a process, means PEVE is greater than PIVI, it can do so at the expense of its internal energy. So as the result, internal energy is decreasing, which is usually accompanied by drop in temperature. If the product PV decreases, the internal energy and the temperature of the fluid will increase during a throttling process. But in the case of ideal gas, because enthalpy is function of temperature only, so the temperature has to remain constant during a throttling process. More details or more analysis about throttling process we will discuss in the chapter dealing with the property relations. See, during the steady flow processes, no change occur within the controlled volume. It means one does not have to bother about what is going on within the boundaries. Not having to worry about any changes within the controlled volume with time basically simplifies the analysis. Many processes of interest, however, involve changes within the control volume with time, and such processes are called unsteady flow or transient flow processes. The relations developed for steady flow processes are not applicable to these processes. However, while we are analyzing unsteady flow process, we should be careful about the mass and energy contents of the control volume as well as the energy interactions across the boundary. Some of the important or common examples of unsteady flow processes are like charging of rigid vessels from supply lines, discharging a fluid from the pressurized vessel, driving a gas turbine with pressurized air stored in a large container, inflation of tires, and even cooking with an ordinary pressure cooker. Steady flow processes continue indefinitely, whereas the unsteady processes start and end over some finite period of time. So in the case of unsteady process, we will deal with the changes that are occurring over some definite time interval instead of the rate of changes, means changes per unit time. The basic assumptions associated with the unsteady flow, or you can say uniform state, uniform flow processes are: the control volume does not move relative to the coordinate frame. There is no work associated with the acceleration of the control volume. All the velocities measured relative to the coordinate frame are also velocities relative to the control surface, and there is no work associated with the acceleration of the control volume. The similar assumption was dealt with in the case of steady flow process. So I think that is quite clear. The state of each mass at each point in the control volume may change with time, but at any instant of time, the state is uniform throughout the entire control volume. Now here, the state of each mass at each point in the control volume, that is changing with the time. But at any particular time, the state is uniform throughout the space or throughout the entire control volume. The state of mass that crossing each of the areas of flow on the control surface is constant with time, although the mass flow rates may be time varying. The overall process occurs during time t. At any instant of time during the process, the continuity equation is dmcv by dt plus summation of m dot e minus summation of m dot I, that is equal to 0. Summation is for the areas on the control surface through which flow is occurring. Now, integrating over time t, we can get the change of mass in the control volume during the overall process. So we are basically integrating dmcv by dt from the time 0 to t, means for the time interval during which the process is occurring, means whether it is the charging of any rigid vessel or inflation of tires or any other process which comes under the aegis of uniform state or uniform flow process. Okay, so we are integrating this term, and what we get, m2 minus m1. Okay, now this m1 is basically denoting the mass of the control volume at the beginning of the process, whereas m2 is the mass within the control volume at the end of process. Now the total mass leaving the control volume during time t can be obtained by integrating the term m dot e. Okay, because m dot e is mass flow rate for the outgoing stream. So we integrate that, so we obtain summation of me. Okay, similar is the case with the total mass entering the control volume during the time t. We are basically integrating the summation of mass flow rates that is entering the control volume, and after integrating you obtain the summation of all the incoming mass flow rates. Therefore, for this period of time t for which the process is occurring, we can write the continuity equation or mass conservation equation for the uniform state uniform flow process as m2 minus m1 plus me minus mi is equal to 0. These sigma signs are basically denoting the summation of the mass flow rates for the incoming or outgoing stream, as the case may be. Now, this energy equation is basically for the steady state steady flow process, for which any energy term is there for at any instant of time. Means every energy term is expressed as energy transfer rate. Now for the uniform flow process, as the process is occurring for a time period t, means a finite time period t, so we are going to basically integrate each term written here for, in the energy equation. So now we integrate every energy transfer rate that was given in the steady state steady flow equation so as to obtain the energy for the time period t. For example, we have integrated the heat transfer rate, we have integrated the energy associated with the incoming streams for the time period, we have integrated the energy associated with the outgoing streams, and we have also integrated the energy within the control volume that was changing for the time period t, and we have also integrated the work transfer rate so as to obtain the work transfer for the entire time period t. Now substituting all these terms after integration in the energy equation, we get this as the equation for the uniform state uniform flow process. So basically the first term QCV is the heat transfer rate occurring for the time period t. The second term on the left hand side is basically denoting the total energy associated with the incoming streams. Then on the right side, the first term basically denotes the energy associated with the all the outgoing streams. Then the second term on the right side denotes the energy increase or the energy change within the control volume during this time period t. And the third term basically denotes the work transfer during this time period t. So that was all for the lecture associated with the first law of thermodynamics for the control volume, and specifically for the steady state steady flow process and uniform state uniform flow process.